Arden Labs, specializing in high-performance software consulting, training, staffing, and development. Welcome to Module 13, Benchmarking. Let's get started with Lesson 13.1, Basic Benchmarking.
Let me show you how to do some basic benchmarking and sub-benchmarking. We're going to do more detailed benchmarking when we get over to profiling, but we really do need to have the basics here before we can do anything more advanced. Now, the idea of a benchmark is to be able to profile your code both for CPU and memory. And that's really where we're going to be focusing here on the idea of how well the code is performing and what are those allocations that are being produced. Because remember, what's slowing down your program is either those allocations, right? Because it's causing the garbage collector to run harder or longer, more stressful, or we don't have the algorithm efficiencies we otherwise could. Now, there's a bunch of things you have to understand when we deal with benchmarking, all right? If we're dealing with the CPU benchmarking, then what's going to happen is we're going to be tying this Go program into the operating system on the SIGPROF event, which means every 10 milliseconds, this code is going to stop, program counters, information is going to get gathered, and then it's going to start again. So your code's always going to run a little bit slower when we're doing those CPU profiles, but it's okay. We're looking for those hot paths. Also, remember something here. The compiler is going to build this test code and build it into a test binary. So since the compiler is getting involved, one of the things we have to worry about are optimizations that could affect our benchmark, right? So we want to make sure that the code is as close to identical as possible in how it is in the production code. We also want to make sure that we're not putting things in benchmarks where the compiler could choose to throw code away. I mean, the compiler uses an SSA backend, static single assignment backend, and there are opportunities if the compiler wants to take it, even if it's not taking it today, to throw dead code away. That's code that the compiler realizes that if it didn't execute, it wouldn't change the outcome of the program. So everything that we do is we want to make sure that what we're testing is accurate. So when we were writing those unit tests, we had functions that started with the word test. Now we have functions that start with the word benchmark. We're also in an underscore test file because the testing tool is going to run this. And instead of a testing T, we're going to have a testing B pointer as the parameter. Now, everything about this test is going to happen inside this loop. And this loop is always going to be from 0 to b.n. Now, the first time when we run this benchmark, okay, what's going to happen is the testing tool is going to be calling into this function. And the very first time it calls into this benchmark function, b.n is going to be 1. After that, it's going to increase b.n by some order of magnitude, like by tens, okay? It's going to be increasing it. And the idea is to increase or find a value of b.n that matches the bench time for this benchmark. So we're going to have a bench time that's set. The default bench time is 1 second. I'm going to change it up to 3 seconds because I have found for these types of tests, going over 3 seconds really gives you a point of diminishing return. There are tests that the Go language team runs that can be as high as 20 seconds. Remember, what does the bench time mean? It means that this test isn't going to end until we find a value of b.n that lets that loop that you see on line 20 run for that full bench time. So even on a 3-second bench time, it doesn't mean the test is going to run from beginning to end 3 seconds. It's going to take longer because it's got to find that value of b.n. Okay, so let's take a look at this test here. In this test, we've got 2 benchmark functions, and we're trying to identify which function performs better, sprint or the formatted version of sprintf. I want you to notice that on line 21 here, we're using sprint with a string hello. On line 32, we're using sprintf, the formatted version, with the formatted version using the same string hello. In other words, when we're running sprintf, we're giving it a string that isn't even formatted. So the question is, which benchmark will run faster and which one will allocate less, sprint or sprintf for this string? Now, for me, it seems kind of obvious, right? Since the sprintf or formatting function has to do more work around formatting, it's probably going to take longer. So let's go ahead and let's run this benchmark and let's see which one actually performs better. So I'm going to go back into the folder where this code is, and we're going to do the go test call again. Now, when we run the go test call, what we're going to say is if you find any test functions, don't run them. There are times where you're going to have packages that have a combination of tests and benchmarks. And if you don't tell the testing tool to filter out the tests, it will automatically run them. So I like using the word none. It's a regular expression. You can put anything you want. But we have to be explicit about the benchmark tests. So I'm going to say bench dot. And I want to see the memory allocations. So I'm going to ask for the bench mem flag as well. So when I run this benchmark, what are we going to see? Well, we see that sprint ran at 76 nanoseconds per op with one allocation to the heap, which was worth 5 bytes. Notice that sprintf ran a little faster. I mean, we're talking nanoseconds, so virtually they're running at the same speed. But there you are, another 16 nanoseconds faster with the same allocations. And that might actually surprise you because we originally thought since sprintf should be a heavier function, it actually should run slower, and it's not. And this is a point that I want to make. You can't assume about performance. If you're guessing about performance, you're going to be wrong. And that's what's so great about the tooling is we don't have to guess. So when we're writing code, we optimize for correctness, right? The readability and simplicity and integrity of things. And then once we have a piece of code that's working, we can come in, do the benchmarking, and not guess, know for sure how things are behaving, how things are performing, what the deal is. So for me, this is really interesting because sprintf actually runs, in this case, 16 nanoseconds faster. It's virtually the same, but there that is. All right, I want to also show you sub-tests in Go, or sub-benchmarks. Remember, Go added sub-testing. They added the same feature functionality to our benchmarks. So here's really the same benchmarks that we just ran, except right now what I have is a single benchmark function called sprint. And instead of t.run, we have b.run. I didn't use literal functions here. I used name functions for our benchmarks. So it's really the same thing we ran before, but I gave it a name. So this is the none, this is the format. I used name functions in this case with one big benchmark called sprint. So what we can do is jump into that folder in here. There it is. And once again, we can just say, run all of the benchmarks. So we can go, go test. If you find any test functions, don't run them. Run all the benchmarks and show me the memory. And again, it's going to run those tests. There they are in sequence. And once again, we know that the name is none. So I could come in here and now just say, you know what? I want you to run the sprint. There it is, sprint/none. It should just filter out sprint none, and it did. And now again, we have the ability to just run just the benchmarks that we want. And there they are. I do not recommend running benchmarks in parallel. One of the big things that is so important, we'll continue to talk about this, is that your machine must be idle when you're running benchmarks. You really want a quiet machine, and if it's not quiet, you're not going to really get accurate results. So in this case, I wouldn't want to do that, but you're seeing how the idea of sub-benchmarks also are applied here in Go.